Standard conversational AI has a significant limitation. It operates entirely in a vacuum. The moment a session ends, the system instantly forgets the interaction, wiping the slate clean for the next user. Here, we see a diagram comparing that isolated chatbot cycle to an autonomous agent. The agent is anchored by a persistent memory architecture, allowing it to evaluate past mistakes and accumulate experience across multiple sessions. Simply generating accurate text isn't enough to handle complex, multi-step workflows. Bridging the gap to actual autonomy requires engineering a reliable memory system. This four-quadrant chart maps how AI memory systems align with human cognitive functions. You have short-term focus, factual recall, learned physical or technical skills, and the personal experience derived from past events. Researchers at Princeton formalized these concepts into the Koala framework. As shown here, it defines four distinct, interconnected memory pillars that serve as the foundational blueprint for a functional language agent. The first pillar is working memory. Think of this as the agent's active scratchpad or computer RAM. It holds the immediate conversation, system instructions, and any manually loaded files. Notice the blue line at the top. That represents the context ceiling. If you stuff this active memory with too many files, performance degrades and the agent loses track of information buried in the middle of the stack. Because working memory is highly volatile and strictly limited by a token budget, agents rely on the remaining three memory types to store their persistent intelligence. The second pillar is semantic memory, visualized here as a filing cabinet storing a persistent markdown file. This is the project rulebook. It holds static conventions, coding standards, and strict constraints. It loads automatically at the start of every session, so the agent never starts blank. While semantic memory stores what to know, procedural memory dictates how to do. This flow illustrates an agent's skill, a folder containing specific, step-by-step instructions for executing complex technical tasks. To protect the token budget, agents use progressive disclosure. Looking left, the agent initially views a lightweight index of available skills. Heavy instructions are only downloaded into the context window when a user's specific request actively triggers the need for that exact tool. Separating static project facts from active workflow execution allows the system to handle complex tasks without instantly maxing out its computing ceiling. The final pillar is episodic memory, the mechanism for genuine cross-session learning. As this comparison shows, simply saving a massive pile of raw conversation transcripts is largely useless for efficient navigation. For an agent, forgetting is a necessary engineering problem. This diagram demonstrates how an evaluation filter processes a raw 45-minute debugging transcript. It discards obsolete data and compresses the useful experience into a single, highly concentrated insight note for future reference. These four memories form an interaction cycle. A task arrives in working memory, the agent references semantic constraints, pulls a tool from procedural memory, and logs the outcome in episodic memory. Test yourself. Which memory types does a basic thermostat need versus a password bot? A true agentic workflow operates as a continuous loop where all available memory systems interact to execute, evaluate, and learn from a single task. Resolving that exercise, this staircase graphic outlines the requirements. A basic reflex bot only needs working memory. A support bot adds procedural memory for its specific task. An autonomous coding agent, handling highly complex business logic, requires all four. This table provides three strict rules for designing workflows. 1. Respect the working token budget. 2. Draft definitive semantic rules to prevent repeating basic errors. And 3. Isolate procedural skills into discrete, heavily documented steps. Here is the consolidated memory architecture matrix. It maps each memory type to its human analogy, core function, and expected lifespan within the system. Take a moment to screenshot or save this matrix. It is your primary blueprint for evaluating future AI tools. Properly architected memory is the bridge that transforms a reactive chatbot into a reliable, autonomous system.